Good morning, my name is Diệu. Today I will present my lesson plan about how to teach the characteristics of free-fall motion. The first thing I want to talk about is the context. The students have learned about the equation of uniformly accelerated linear motion, the definition for free-fall motion, the direction of free-fall motion, and the motion of an object moved down an incline. And the goal of the lesson is about the knowledge is the characteristics of free-fall motion. It is uniformly accelerated linear motion, and I want students to gain two skills, that is design the experiment and carry out the experiment and collect the data. And the third part is teaching strategy. There is three phases in this part. The first one is elicits the problem. The students have learned about the direction of free-fall motion, but they do not know how the distance that the object fall down depend on time t. If we know this relationship, we can conclude about the characteristics of this motion. So the question is, what is the characteristics of free-fall motion? The second phase is the problem solving. Firstly, I ask students to give the assumption about the characteristic of free-fall motion. In a previous lesson, a student investigated the motion of an object move down an incline, and they know that the object the motion is uniformly accelerated, and if we increase the angle until 89, it's still uniformly accelerated. So if the angle equals 90 degrees, what happens? At this angle, the object will free fall, and student will assume that the object still fall down with uniformly accelerated. To prove this assumption, they have to choose the consequence to verify. If the object moves with uniformly accelerated motion, the equation between the distance s and the time t is 1/8 squared. This is the simplest case with the initial position and velocity equal to 0. So the consequence here is the distance s directly proportional to square t, or s over t squared equal constant. This is the consequence we need to check, and to check this, we have to measure the distance s and the time t. So what equipment we need to use to do this? Student will guess that we need to measure s and t by linear rule and a stopwatch. And I get a experiment design like this. There is a light track with a ruler here. There are two photo gates. An object hold at this position. It can fall from photo gate A, photo gate B, and two photo gates are connected to a digital timer. Then I asked students to compare the design with the real setup. The real setup has some more detail, such as a magnetic magnet and a box to hold the object. Then I asked students to carry out the experiment and collect the data. If they carry that s over t squared equal constant, so the free fall object is uniformly accelerated linear motion. So now I do the experiment. Electromagnetic, hold the object, and then I push this button. It's
I have the same commentation. You should use the value that student can simply more clearly recognize that the consequence is proof.
So what values of S now?
Yeah.
What
value of S?
I choose the value of S is 50 centimeter.
50
centimeters.
And the next one?
And the next one is 60. Firstly, I will as 5 centimeter.
You spend time. You have two value of S. You should use two value of S, and which value of S should or what value of S should you choose? Two value.
I choose the 50 and 20 and 50.
20 and 50 might know clearly.
S.
Now, you mean it's S, finally S is directly proportional to D squared.
Yeah.
So it's increased 4 times, and student can easily see term increase 2 times.
Yeah.
So the data table is much more sensible for students rather than random data and they have to calculate manually. So better to choose very specific distance S, and then the student can see some change in term vividly. So we recommend some distance like 5 centimeters, 25 centimeters, and something. And 25 times 5. So cubics of 5?
Sure. 5.
125 is long enough, something like that. So, I mean, so student can see the change of Tom,
Yeah.
according to the change of the distance.
Yeah.
What do you do?
Yesterday I say you make your class is sleepy. Yeah. You must focus on this and say now this is right or wrong. When it's right, S1 is 20. S2 is 420.
80.
80. And when this is right, it must be T1. Here is or T2 should start. And do it. It makes more clearly. Yeah. And I see all of you don't use here. You use directly. It's too soft. Why don't you other electric curve? Yeah.
So the extensible electric circuit.
Oh.
Yes, and you can see, you can write down here, T1 is, and you can say, when this is correct, T2 must be, how much? You must ask the student, when this is true or correct, T2 must be. And now do it. And all of the student is focused on this and decide this consequence is right or wrong. It make a very dramatic moment. And you make all the thing is boring. Now it's double. Not
So we measure that T2 equal 0.405. We have T2, T1 approximately equal to. So this consequence is right. So we can conclude that the free fall motion is uniformly accelerated linear motion. That's all.
Finish?
Yes.
Okay, so you know something about, you have to really think about what is the set of data you plan to collect. It should be specific data.
Yeah.
And when students look in that, they do not really have to use the calculator, they can still predict something or split something. Rather than to just say, take randomly the values and do a lot of mathematical calculation for fractional s over t squared. Boring. It's math lessons.
The most important thing of experiment is used for a dramatic moment. So other we don't implement.
Yeah.
Especially for the demonstration, you are at the center of the stage and all the people looking you, so you have to make things really fun. And if you let students do experiments in groups, so they can do a lot more details and more carefully collection of data and so on. But here you are at the center of the stage, so you have to show up, think, and let's make the classroom environment fun, rather than just prove something.
Yeah.
Okay? Good. So the next one. Thank you.